Good audience already joined, so maybe we can get started here. So yeah, it's a great pleasure to have you, Mohammad, to our ICON seminar here. Just to give you a quick overview, ICON is a relatively new center here at Purdue, Center for Innovation and Control, Optimization and Networks. We're a very big school here at Purdue with many faculty across engineering and computer science and polytechnic math, working on many aspects of autonomous systems. So we formed ICON essentially as an organization to bring together all these people in one place to be able to tackle these kinds of challenges, talk about emerging topics and so forth. So, it's wonderful to have you here. So I'm going to turn it over to Abulfaz Hashemi, who will introduce you.
Thanks, Elias. Hi, everyone. It's our great pleasure to have Dr. Mohammad Ghavamzadeh from Google Research as our speaker today. Dr. Ghavamzadeh received a PhD degree from University of Massachusetts at Amherst in 2005. He was a postdoctoral fellow at University of Alberta from 2005 to 2008. And then he was a permanent researcher at INRIA from 2008 and 2013. He was a recipient of the INRIA Award for Scientific Excellence in 2011 and obtained his habilitation in 2014. Since 2013, he has been a senior researcher at Adobe and FAIR, and now a senior staff research scientist at Google. He has published over 100 papers in major ML and AI conferences and venues, and he has co-chaired a number of workshops and tutorials and NeurIPS, ICML, and AAAI. His current research is focused on reinforcement learning, bandit algorithms, and recommendation systems. Without further ado, I welcome Mohammad to start his talk.
Thank you very much for the invitation and also for the nice introduction. As I mentioned earlier, because of the diversity in the group, I decided to talk about something more practical today. I hope this is a good choice and everybody can connect with the talk. So the talk is about mirror descent policy optimization. This is a work that I did with three of my former interns that are now doing PhD at University of Alberta. One is at Technion and one is at Microsoft Research in New York City. So this work has been accepted this year at ICLR, but the code and blog post and all the related stuff is available online, and it's going to be in my last slide, so you can access the code and the long paper and everything there. Okay, so let's start with the outline. So I'll give you just a little bit about the motivation behind this work first, and then I'll tell you about Markov decision processes, but I assume that you all know about it, just to establish the notation. Then I'll talk about mirror descent methods from optimization and how it's been used in reinforcement learning. And then I focus on the algorithm that we have developed and both the on-policy and off-policy version of the algorithm. And one important part of this research, which was actually very eye-opening for me, was to look at popular algorithms like TRPO, PPO, and soft actor critic from the lens of optimization and try to understand why these methods are successful and under which circumstances they work well and so on and so forth. So that part was also, at least for me, was very rewarding too, because these days we are developing a lot of algorithms from heuristics. Of course, some of these heuristics probably are not, that relevant, and they're just working in certain scenarios, but some of them are very smart, and it would be very interesting if we can explain them from the basics of mathematics, either from dynamic programming, optimization, and other related areas. So that's very rewarding. And then there are some experiments, because as I said, this is an experimental work, it's not a theoretical work, which supports our finding, and also I would like to share what we found in these experiments. Let's start with motivation. So trust region methods are known to perform well in reinforcement learning, for policy optimization and reinforcement learning. So the idea is when you update your policy parameters, you update it within a trust region around the old policy. Basically, you're trying to get better, but you don't want to move away too much from your current strategy. And the rationale behind this is since in reinforcement learning, it's impossible that you do something without implicitly or explicitly estimate the value function of the current policy or the advantage function for those of you who are more familiar with the details of RL. And this restriction or constraint that we apply to the two consequent policies helps us to have more accurate estimation of the advantage function or value function of the current policy. So this idea all started from the theoretical work of John Langford and Sham Kakade on conservative policy iteration, CPI, and then it was popularized by developing practical algorithms like TRPO and PPO by John Schulmans and a lot of other algorithms with this theme and flavor in the last couple of years. Okay, so now what is mirror descent? So mirror descent is also a relatively well understood technique in optimization. And recently people have studied that the importance of mirror descent in policy optimization, and they used it to analyze the trust region RL algorithms. So these are the two papers by from Matthew Geist and the group in France, and also some of the groups at Technion. There are also other work in this area that they try to use mirror descent to analyze these trust region algorithms, but it's been very limited to tabular formulations and but the results are very promising. So basically shows that this is a good tool to explain these trust region algorithms, to understand them better. So the motivation behind this work was, which was motivated by this theoretical findings, was how to derive scalable and practical RL algorithms coming from this mirror descent optimization principle, and basically going beyond the tabular formulation, and then also use this tool to better understand and explain the existing popular and successful algorithms like TRPO, PPO, and soft backward proving. So that's the motivation of this research. Let me start with some preliminaries and notation. So let's start with Markov decision process. I just used one slide. I know you are all familiar with MDPs. I just want to establish the notations that I've used in the paper. So S is the state, A the action, P is the dynamic, R the reward function, gamma discount factor, and mu I use it as the initial state distribution of the system. Policy has been represented as pi, which is a mapping from states to distribution over actions. A state occupancy measure is basically the gamma state distribution of when you follow a policy, how you visit the states of the environment, and how much you spend in each state, of course, discounted by gamma. Value function has been represented by V of pi, the value function of policy pi. Action value function is has been represented by Q, and advantage function is the difference between these two functions. Is this level good, or should I explain the meaning of value function and action value function, or I think,
Mohammad, I think it's good.
It's great.
Okay.
Yeah.
Great. So there is one, only the last bullet that I would like to emphasize a little bit more is there is this notion of soft MDPs or entropy regularized MDPs that is very popular, and people are looking at it from different perspectives. There are some psychological reasons for why the reward function should be divided to a reward signal and an entropy related signal. There are also some motivations from optimization and about it, but the simplest part of this is in soft MDPs, you add a new signal to the reward function, which is you basically make the reward function as a combination of the standard reward function and an entropy related term, which is related to the current policy. So you can think of it in a very high level that in addition to doing something good, being explorative should be also rewarded. So if you add to the entropy and try to explore, then you should be also be rewarded in addition to doing something good. So you can think about that green term, which is the entropy related term, as the reward for more exploration. So when you solve an MDP of this form, a little bit the equations and everything changes, and this is why we call it the soft MDP, and it's being used in many practical algorithms these days. So this is the only part that probably some of you may not be quite familiar with. So let's start with mirror descent, which is kind of like the main optimization tool that we are using in this work. So mirror descent is a first order trust region method for constrained convex optimization. And when I use the word convex in this talk, read it as either convex or concave, depending on whether we are doing minimization or maximization. Because in MDP, we can do cost minimization, or we can do reward maximization. So I use convex and concave in a kind of like alternative way in this talk. In constraint problem, you would like to basically find the maximum of a function when you want to constrain yourself to a set C. So C is the constraint set, F is your function, and you're trying to maximize or minimize that function in that region. So the mirror descent update basically has two parts. At each is an iterative algorithm, and at each iteration, the new point that you derive is the result of an optimization problem. And the objective function of this optimization problem consists of two terms. One term is the linearization of the function around the current point. As you can see, the red term is the linearization of function f around the current point, which is xk, because we are at iteration number k, plus a term that is a Bergman divergence with respect to the current point. So this is basically defining the trust region penalty using this Bergman divergence. And Bergman divergence, you see the formulation there. Bergman divergence is usually associated with a strongly convex function psi, and when you change psi, this Bergman divergence changes, and this way you can basically control the form of your trust region or your constraint or your penalty term. Okay, so what is happening here? You're turning an optimization problem or a constraint optimization problem to an optimization without constraint by adding a penalty term, and this penalty is appearing in the form of the Bergman divergence. So depending on what this psi, which is like, you can think of it as the kernel of this Bergman divergence, is the notion of Bergman divergence changes. So if this psi is Euclidean norm, then the Bergman divergence becomes Euclidean distance. So you define your trust region using the Euclidean distance, and then the optimization, the mirror descent update becomes something they call it projected gradient descent. If this psi is the negative of the Shannon entropy, then the Bergman becomes the KL divergence, which is probably the most popular form of defining this trust region, at least in the reinforcement learning community. And then it becomes like an exponentiated gradient descent algorithm. So a little bit, since I told you I got motivated by the theoretical results, I tell you a little bit, because this work again is not about theory, but these results are promising in the sense that when in the results that, as far as I know, in optimization, if f is convex, this procedure is going to have the rate of 1 over root square of k. If f is strongly convex, then we get the improvement and the rate is 1 over k. And if f is replaced by two terms, one is a term that is not strongly convex, plus lambda, a term that is strongly convex, g, then we get a fast rate of 1/k, but we add a bias. Basically, we are converging to something that is different than the original minima or maxima of the function, but we converge with a fast rate. So these are the results from mirror descent. And there is one more thing that is interesting, and we are using it later in this work, is if your constraint set C is the unit simplex and your Bergman divergence is KL, then this optimization problem has a very nice exponential closed form of the form that you can see in this slide. And I put this here because I'm using this update later in the work. Okay, so now see how this mirror descent has been studied in RL. First the question is, okay, what is the objective function in RL? What is the thing that we are trying to optimize in RL? So in RL, we are trying to, we look at basically two forms of optimization. The first form of optimization is a form that is very common in value function-based algorithm, that we are looking for a policy. We are looking for the optimal value function. An optimal value function is a function over the state space that has the maximum value at all states. And the corresponding policy is the optimal, the policy corresponding to that value function is the optimal policy. So basically we are optimizing over all states. The other optimization criteria that is very common in policy optimization is only optimizing at the initial state of the system. As you can see, we are still optimizing over the value function, but not at every state. Only expectation when state is coming from the initial state distribution of the system. So this is usually the objective function that we are optimizing in policy gradient or policy optimization techniques. Okay. So if I turn this to a kind of like a mirror descent style of optimization, you're going to see two different optimizations here. One corresponds to the first optimization, that is updating for all states, and the other one corresponds to the second one, which is updating or optimizing only for the initial state of the system. And what is important here is this policy class, capital Pi, basically is the space that you define for your policy. Depends on your policy parameterization. Is a neural network, it's whatever it is, so it's restricted. It's not all possible policies. It's restricted to the class of policies that you decide to use for your algorithm. And this is the advantage function, this is the KL. So I've written this specifically for the KL Bergman divergence, but you can write it for the others. And I call this off policy and on policy because in the first case that we are, in the second case that we start from the beginning of the system, we execute a policy and we want this to be optimized for the states that are coming according to the stationary distribution of the current policy. Right? So this is why we have a policy, we execute that policy, and then we use that data to update the policy. So the data is completely generated from the current policy. This is why we call it on policy. In the second case, as you can see, there is no restriction that the data is generated according to the stationary distribution of the policy. And this is why we call it the off policy. You usually go to your replay buffer and you sample from that, and the data can come from many different policies or whatever is in your replay buffer. So this is probably, if you're familiar with RL, you're familiar with this concept of what is on policy and what is off policy. And when we develop our algorithms, we have both off policy and on policy version. For on policy, this is the optimization criteria that we are using. And for off policy, the first one is the optimization criteria that we are using. And it's very easy to see that these two corresponds to the two objective functions that I defined at the beginning. So one thing that was shown and was very motivating to me by these guys who studied mirror descent RL in the tabular case is they proved the same convergence rate for tabular RL as what we can get in the optimization. You remember, if the function is not strongly convex, we can get 1 over root square of k, which is k is the number of iterations. And this has been derived also for the tabular RL formulation. And this is very promising. It means that by using mirror descent from optimization in reinforcement learning, we are not losing in terms of the rate of convergence. And this is actually good. And we said, okay, let's now try to build on top of this and go beyond the tabular algorithms to more practical methods. Also, okay, another result that these guys showed, which is interesting, is they also turned the MDP from normal MDP to that soft MDP. And they showed that, oh, you can get the 1 over k to a biased solution. You remember in mirror descent, I mentioned that if you replace the objective function with an objective function that has a strongly convex term in it, you can converge with fast rate of 1 over k, but to a biased solution. The same thing is happening here if you move from the, let's say, hard MDP to soft MDP. And soft is the entropy regularized MDP, as I explained it earlier. So these are all positive results that we found. And as you can see, when we go to soft MDP, these equations change a little bit. I don't want to go to the details. The derivation of this is pretty standard, but since the reward function now has an entropy term, these optimizations are changing a little bit. This is for the hard MDP, and this is for the soft MDP. Anyway, okay, any just question up to this point about the motivation? I just talked about the connection between mirror descent and quality optimization in RL. Any question that I can answer at this point?
Yeah, so, sorry, go ahead.
Okay, this is Shai. I do have a question about your, you say the project gradient for in the MD, the mirror descent. I believe, I noticed that there is more like, you could call it a step size TK there, right? 1 over TK. So do you have any idea or insight on whether how to get rid of this kind of thing? Because this will lead to asymptotical convergence rather than exponential convergence.
So in the theory of mirror descent, as again, I'm not an expert in optimization, but as far as I know, the schedule of TK is very simple. You just define it as if the total number of iterations is capital K, you just need to define it as K over, or 1 minus K over K, which basically at the beginning you set it to 1 and gradually goes to 0. And as you said, it's an asymptotic convergence, but we can get, and this is actually a positive for our algorithm, because unlike TRPO and PPO, and this is something that I'm going to mention later, they have a lot of problem with hyperparameter tuning. In our algorithm, we use the same schedule for T from the theory of mirror descent. And we didn't need actually to fine tune this TK that much in our experiments.
I see. So basically, this 1 over TK plays a role because you have 2 terms on the update and to coordinate the 2 terms and to get equilibrium. Otherwise, there may not equilibrium. So this kind of things is, I would be doing this more thing about this, you know, especially in multi-agent case, if all the agents share the same step size, that may cause a problem because all the agents may have a different clock about the TK. So we are trying to say whether there will be a method to eliminate this 1 over TK such that we could get exponential convergence or algorithm and without sharing this kind of step size, sharing the clock things. That's more like why I asked this question.
I haven't thought about this in the multi-agent framework, but this is definitely important. We know the role of these step size can be very crucial in algorithms.
Yes, exactly.
But the thing that was nice, and actually one of the nice properties of our algorithms, is at least for this parameter, we didn't have to do too much tuning. We just followed the theory, and the results, it was not sensitive, the results, at least to this parameter.
Yeah, I believe with any
and go to
alpha
deep
k,
reinforcement learning, which has a lot of parameters. If you just say, okay, at least I don't have to be worried about this one is good.
yes, definitely. You know, this similar to I think a generalized version will be any alpha k, and then it goes to 0 alpha k, and its integration is not bounded, but its square integration is it's bounded. That will be fine, I believe. But tk is definitely tk equal to k is definitely a very intuitive and simple choice. If it works, yeah, definitely we'll choose this for simplicity. Yeah. Thank you. So I'm
Let's
sorry.
One more question, because I want to go back to the thing, but if any
Yes.
other question, please.
No, there was a, I think, clarifying question in the chat about K, small k versus capital K. Yeah, in your convergence results for MDP in the RL.
So capital K is basically, you can think of it about the horizon of the problem. And for any capital K, you can basically get a rate of how fast you're converging. And small k is the just a notation for the current iteration. Any other question? Okay, let's move on. I'll be happy to answer questions at the end if. Okay, so now let's look at our algorithms. The algorithm that we have is actually the concept is very simple. So as I explained, this is the optimization problem that we have to solve at each iteration, because mirror descent is an iterative algorithm. From one policy to another, we have to solve these optimizations. But if you are in on policy, the second optimization, in the off policy, the top optimization. But when we go beyond the tabular RL and we formulate everything in the form of function approximation, then this problem cannot be solved easily. And when we cannot solve it, then the question is, what should we do? So the main idea of these algorithms that we call the mirror descent policy optimization is, okay, at each iteration, you have an optimization problem. You cannot solve it in closed form. Let's take multiple steps in towards minimizing this objective function. So basically, you can say, instead of solving it exactly, just solve it in an approximate form. So this little m is the parameter that I apply the gradient for m steps for each optimization problem. So instead of solving it in closed form, I approximately solving it by taking m gradient step or a stochastic or a SGD steps towards the minimum of that objective function. See, the idea is pretty simple. As you can see, theta k is the current policy. We start from this, we do this update m times, and then after m times, we return whatever theta we have as theta k plus 1. So that's the whole idea. So how it's applied to on policy and off policy algorithm, I go for the on policy. So in the on policy, this is the objective function. Remember, the states are coming from the stationary distribution of the current policy. So this means that when you have a current policy, you have to execute it for a while. This is the on policy form. And this is basically the objective. This is how we do the update. We do it for m steps. The gradient of the objective function looks like this. Don't go to the details. The deriving these the gradient from capital psi to the equations that you see here is pretty standard. For those of you who have worked with TRPO and PPO, you can derive this much faster than I do. It's don't go to details. It looks ugly, but this is pretty straightforward. The only thing that is important is taking this m step here and moving forward. And one thing that is very crucial here, and I think the main message that you should take from here is, if you take one step instead of m step, since this KL gradient is going to be 0, what this algorithm is going to be reduced to is going to be reduced to vanilla policy gradient. Suddenly, you move from something more sophisticated to vanilla policy gradient, because this is the objective function that's optimized with vanilla policy gradient. So this is not good. So if you take it with m equal to 1, you're doing something very, very simple. But if you add using a m larger than 1, then it's going to be. you see the effect of this. So this is also, this reduction to vanilla policy gradient is important if m is equal to 1. So this is just the pseudocode of the algorithm. Again, if you're familiar with TRPO type of algorithm, you read this pseudocode better than I do. If you are not familiar, then don't worry. This is the details, but as you can see, this is the style of this algorithm is very similar to TRPO. You have a current policy theta k. You execute this for capital M step. This capital M is different than the little m. So basically means you generate M trajectories, M steps following this policy. You calculate the return, you estimate the advantage function for all these things. And then using that data, you update your policy for little m steps by taking gradient update, and then you also need to estimate your value function, because these algorithms are really actor-critic type of algorithms. So you have a critic, which is, you have an actor, which is the controller that you update here, and you have a critic for the value update that you're updating it here using some mini batch of data and neural network that you're using to represent the value function. Okay, so this is exactly the form that you, it's very similar, this part that you collect the data, this part that you optimize your critic is very similar to TRPO, but the actor update is different. Okay, so this is the algorithm. So now let's see how it compares with TRPO and PPO. Let's start with TRPO. So TRPO and PPO, they are trust region algorithms. The way that they enforce the trust region is different. TRPO is enforcing it in a more explicit way, in the sense that they are searching for the new policy using some line search. They generate the new policy, then they check the KL explicitly and say, oh, if the KL between the new policy and the old policy is bigger than something, you go back to the controller and say, this is not a good suggestion, suggest something else. And usually what they do is they reduce the step size, they come back with another policy, you do the KL test and check, and then eventually you say, okay, what you suggested is good, is within the KL distance, so I accept it and you go. So this is a kind of like using a line search to explicitly enforcing the trust region. So this is the whole idea of TRPO, and as you see, the critic, the actor part, the controller part is different than our algorithm. In our algorithm, we don't solve a constraint optimization problem. We just add a penalty term and do m steps of gradient update. Here, they are enforcing the constraint very heavily by doing this kind of line search. So now, let's see what is the differences. As I mentioned here in TRPO, the constraint is hard. In our case, the constraint is basically only applies through a penalty term. In the optimization in TRPO uses a natural gradient. This f function that you see is the inverse of the Fisher information matrix that they are using. We just use simple SGD. Of course, this looks like that TRPO is going to be very expensive because of this, but this is not the case. They have a way that they calculate this in closed form. So really this doesn't add too much weight to TRPO. The KL direction is different. We are using the reverse KL direction, which is consistent with what is happening in mirror descent, but TRPO uses the forward direction of KL, which is the opposite direction. The step size related to the question that was asked in TRPO is a heuristic, and tuning this is very important because, as I said, they keep reducing this step size by some schedule if the suggested policy doesn't pass the KL test or the trust region test, and they change this thing. But we use simply using the simple annealing coming from the theory, and at least we didn't find too much sensitivity to this part in our algorithm. So these are the differences with TRPO.
So Mohammad, question: This sure. Small k you had is inner loop optimization.
It's the inner loop,
right? Okay, gotcha.
Yes. And so I skipped this. This is actually no. Let's talk about it. It's interesting that the PPO paper. It was an algorithm at the beginning of the PPO paper that they called it. We call it KL PPO. I think they use it. Maybe other definitions for it. This KL PPO was very similar to our idea of MDPO, but they didn't go to the details of this KL-PPO. They just showed some experiments and showed it doesn't work, and they moved on to the real contribution of that paper called PPO. So when we look at that paper and said, oh, these guys have done this already, but then we look at the results and say, okay, this doesn't look promising and that's not consistent with our finding. So honestly, this KL-PPO has not been published. There is no very clear code available for it. So I can just conjecture why it didn't work, and in our case, things work. One is these guys use mini batches for gradient updates, while we are using the entire data. They use some heuristic for their schedule. We used basically the annealing from the theory. The direction of KL was different, which this one I don't think has any effect on the performance. And it's not very clear what is the M that they are using in their work. But I'm just trying to say that something very similar to MDPO was proposed in the PPO paper, but never pursued and properly executed. So, for those of you who have seen this, I just wanted to mention that. So now let's go to PPO. So PPO, unlike TRPO that enforces the constraint in a very kind of like very explicit way, doesn't do it in an explicit way, but they try to do this by kind of like clipping of the ratio of the current and the new policy. So this is kind of like a soft way that PPO applies the constraint, and also takes multiple SGD steps for this unconstrained objective. So basically they start with a constraint, they turn the constraint to an unconstrained by adding this clipping, and then they handle the trust region case very differently than both TRPO and MDPO. So one thing that is interesting here is this clipping, there is no proof that it can really enforces the constraint. It just increases the probability that constraint is being satisfied. And this is something that has been noted in the community, that PPO has no proof that constraint is really being satisfied. It's just increasing the probability that it's being satisfied. And one thing that we discovered in our experiments, and I'll talk about it a little bit more when we go to the experiments, and it was also pointed out by a very, like in some ablation study by the Alexander Madri's group, is most success of PPO is not because of the algorithm, is because of the code level optimizations, and particularly the use of generalized advantage estimation that they do in the code. So these days, I think the word has changed, that there is an algorithm and there is a code, and the difference between the algorithm you see in the paper and the code could be huge. And there are a lot of code level optimizations that people are using, and the practical version of these algorithms that are out there is using this code level optimization. So what we discovered, and is consistent at least with the finding of Madri, is PPO by itself is not a very successful algorithm. These code level optimizations that I tell you about them a little bit more are playing very important role in the success of PPO. Okay, so this is the connection of our algorithm with TRPO and PPO. And what is really important here is we are neither enforcing the constraint in a kind of very explicit way that TRPO does. We are not doing it by this clipping trick. We just enforce the constraint in an implicit way by adding a penalty term and approximately solving this problem. So we are doing kind of like an stage, we are approximately solving the update of mirror descent. So now let's go to the off policy case. In the off policy case, as you remember, the optimization problem is a little bit different. Here the states are not coming from the current policy, they are coming from a data set. And usually in these algorithms, this data set is the replay buffer. So these states are coming from multiple different policies. So this is why we call it off policy. And then it's very common that you take this, they do this trick, they call it the optimization trick, And by doing this reprogrammation trick, you can easily open up this term. The first two terms are when you open up the KL, and the last term is if you manipulate this advantage function a little bit. And this A tilde is basically the action that is coming from, let's say, the mean of the policy network plus the noise that is from the Gaussian. So this is kind of like a noisy action, which is standard in when you're using reparameterization tree. And then, as I mentioned, these algorithms are all actor-critic type of algorithms. So you need to you need to also estimate the value function and action value function. And we are basically having explicit representation both for value function and action value function, similar to what happens in soft actor-critic algorithms that if you are familiar with. So this is again the pseudocode of the algorithm. Similar to the on-policy case, if you are familiar with soft actor-critic, you can read this pseudocode much better than I do. If you are not, then don't go to the details. What is important is here, you take an action according to the current policy, and then you add this tuple to the replay buffer, and then you go to the replay buffer and you sample a mini batch from the replay buffer and use this mini batch to do your actor update or controller update, and to do your critic update, which is learning the value function and action value function. What is important is similar to soft actor critic. We have an explicit representation for the value function, and we have an explicit representation for action value function. And what is different is our controller or actor update, which similar to the previous case, we take the objective function and we take M gradient steps for approximately solving the mirror descent update. This is the whole idea of the algorithm. Let's look at the connection of this to soft actor critic. So soft actor critic has never been introduced in the literature, unlike TRPO and PPO. Soft actor critic has never been introduced as a trust region algorithm. Soft actor critic has been introduced as a approximate dynamic programming algorithm for soft MDPs. And what is happening is, as you first try to evaluate the action value function or the soft action value function of your current policy, and then you know that in soft MDPs, the greedification gives you this kind of like an exponential update. But then the problem is this pi k plus 1 that you obtain may not belong to your policy space, so it may not be consistent with your controller. Then you need to do a projection and bring it down to the space of your policy. And this projection is done by just minimizing this k. So this is one way of looking at how soft actor critic works. So if I look at this optimization problem, do the reparameterization trick, this is the objective function that this not curly L, the normal L SAC is the optimization problem that soft actor critic solves at each step. So now, if we look at the optimization or the objective function that off-policy MDPO optimizes and comparing it to the SAC one, we see that, oh, these two terms are the same. This red term is extra in the objective function of off-policy MDPO. Okay, so how we want to explain this? In order to explain this, I've tried to use another derivation for our off-policy MDPO algorithm to see this difference nicely. Remember, at the beginning, when I was explaining to you the basics of mirror descent, I told you if the constraint set is the simplex, then the update has this nice exponential form, right? So now imagine that if my policy class is all stochastic policies, this is my update. So my update, so this is my the object optimization problem that I'm solving at each iteration. So my new policy is going to have this very nice closed form. Okay. Compare this with SAC. We have this extra policy here. So in our update, we have the current policy. In SAC, the current policy is not there. The rest is similar. This is just a normalization term. The SAC normalization is there. Here is the same. The only difference is this policy. Okay. So now, but of course we know that this our policy class is not the entire stochastic policies. So we need also to do some projection. And if we do this projection according to the Bergman divergence that we have been using, which in most of the case we are using KL, then we're gonna end up with this objective function. And if we do the reproposition trick, it's gonna give us this objective function, the one that you see at the end. Now let's do a comparison. Our update looks like this, SAC update looks like this. We have this extra current policy in the update. When we go to the objective function of the optimization, we have this extra term. So what does that mean? Basically, this tells us that if we want to look at SAC from the lens of trust region algorithms, SAC can be seen as a trust region algorithm, but it doesn't try to make the new policy close to the previous policy, like what we do here, but it tries to keep the new policy close to uniform policy. And what does that mean? That means that SAC, by doing this, injects some form of exploration to the algorithm. So in our case, we are trying to keep ourselves close to the previous policy. So the trust region is defined with respect to the previous policy. In SAC, the trust region is defined with respect to a constant, which you can think of it as a uniform policy. So this basically says to SAC that, oh, go optimize yourself, but remember, remain explorative. So this is to me, that was interesting that we can easily look at SAC as a trust region algorithm with this notion of trust region. And this is nice. There is another discussion that probably we're not gonna have time to discuss it, and I don't have a proper answer for it, is whether SAC should be looked at as an approximate policy iteration algorithm or an approximate value iteration algorithm. This is also a very interesting question. So even looking at SAC from approximate dynamic programming point of view is not very clear. So this is another way of looking at it, which to me was interesting. If we want to summarize the comparison with SAC, in SAC, as I said, they constrain the current policy to be close to uniform. We constrain the current policy to be close to the previous policy. And the projection step in SAC paper, they just say you can heuristically choose this projection. They just decided to choose the KL. But what is important is your projection should be consistent with the choice of the Bergman divergence that you're doing. So if you think about this problem from the optimization perspective, it's not arbitrary projection. Whatever projection you pick should be consistent with the choice of your Bergman divergence in your formulation. Okay, so this is this. Let's go to the experiments, and I go very fast for the experiments. So the first part of the experiments, as you can basically say that, okay, your algorithm is nice, but has a hyperparameter, this little m, which is how many gradient steps I have to do at each step. And you advocated for more than one. And I say, okay, the first question is, this is a hyperparameter of our algorithm. And we should see how sensitive our algorithm is with respect to this hyperparameter. So we basically did a lot of experiments on the Mujuko domain, and we have recently experiments also with Atari. So for the on-policy algorithm, definitely m equal to 1 didn't work well. So basically, it's not surprising if you notice that I said m equal to 1, everything reduces to vanilla policy gradient. M equal to 10 was relatively robust over at least the Mujuko domains. So this was not a very nasty hyperparameter. Nasty means very sensitive hyperparameter to tune. And the same thing for the off-policy case. Of course, the notion of off-policy and on-policy is a little bit different. I can tell you in details, but also what I'm trying to say here is this little m still is a hyperparameter, but it's a quite robust hyperparameter for our algorithms. But you should stay away from 1. That's very important. And we tried these multiple SGD steps for TRPO and didn't help for TRPO. So this is again for those people who are more interested in the practical part is a message. So the experiment that we have done, I mentioned these code level optimizations. So these code level optimizations are 8, 9 of them. That is quite standard. I'm not, a very big applied person. Those of you who are doing things in application, you probably know much better. So some of the observation normalization, reward normalization, value function clipping, learning rate annealing, orthogonal initialization of the weights of the neural network, and also this variance reduction through generalized advantage estimation. These are standard code level optimizations. And this is why we basically implemented 3 versions of all these algorithms. One is the vanilla version, which is the paper version without these code level optimizations. The other one, I call it loaded, which is the algorithms with these code level optimizations. And the third one is loaded plus GAE when we have the GAE as well. Because we noticed that such a kind of like a comprehensive study of these algorithms is kind of missing. So probably paper of Alexander Madry is one of the exceptions, but most of the papers, they don't talk about all these. So the results of all this is in the paper, in the appendices of the paper. So there are a lot of experiments there. So these are the on-policy results that we have done with minimal and loaded. And the comparison is with TRPO and PPO, because these are the on-policy algorithms. This is the table that is summarizing over 6, 7 of these, I think 6 of these Mujuko domains. And you can see that MDPO is performing relatively well. And also I summarize our discoveries in one slide, don't worry about that. Just see that it's performing on par or better than these algorithms. And the difference in the vanilla case is much more. And this is where I was telling you that some of these algorithms, their vanilla version is not actually that good, especially for PPO. TRPO was better or was more robust to adding or removing this policy code level optimization techniques. And then we also applied in Atari. In Atari, we compared with PPO because the literature basically already said TRPO is not that good. For 15 of the 21 games that we tried, we are on par with PPO. In 6, we performed better than PPO. So I can say in Atari, we've been competitive with PPO. I don't want to basically go too far, but these are the key observations that we had from our on-policy experiments that, as you can see, was massive. We looked at vanilla, loaded GE, and all these things. So one thing that we noticed is MDPO performs better than or on par with TRPO. So this has this message to me that this explicit enforcing of the trust region constraint done by TRPO is not really necessary for the success of the algorithm. MDPO performed better than PPO. MDPO reduces the wall clock time more efficient than TRPO. So all these enforcing stuff that TRPO is doing adds to the wall clock time of TRPO, which MDPO doesn't have that. TRPO consistently performed better than PPO. And this is, to me, was shocking because at least literature is advocating more PPO than TRPO. This is in contrast to the common belief, but is in line with some of the results of the Madry's group. And PPO is also gets much better when you add those code level optimization, but PPO is also has the instability. So if you look at the good PPO, they stop the experiments at some point. In some of these domains, if you continue PPO, suddenly the performance drops really badly. So if you stop it at some good point, you're good. Other than that, you don't know what's going to happen. It was not in all domains, but it happened in some domains. So it has this kind of instability that we observe. So now the off-policy results, we compared our results with soft actor critic. One thing that we did, and just mention it very briefly, but I would be happy to talk to you offline because we are almost out of time. We try to also change the notion of the Bergman divergence. And we moved from KL to Sallis entropy. And we wanted to see when we go to Sallis entropy instead of KL, what is changing in these algorithms. And as you can see that at least in Mujuko domains, in some of the problems, MDPO with KL, which is equivalent to Sallis when Q is equal to 1. Because this Sallis is a family of entropies that at Q equal to 1 is basically coincides with Shannon entropy, and we become basically, the Bergman divergence becomes KL. At Q equal to 2, it becomes something that is called basically the sparse version of Sallis entropy. So you can see that in some domains, KL was optimal, so Q equal to 1 was optimal. So adding this extra hyperparameter and tuning didn't help. In some domains, actually playing with Q helped. But we are far from understanding, or at least I don't have a very good understanding of this family of entropies, which in the context of RL, how they help. So far, we studied it as like a hyperparameter and tune it, and it helps, but whether with the cost of tuning an extra parameter is worth it, I don't know. Definitely more study is needed. So what we discovered, or what we observed from our experiments, MDPO performs better than or on par with SAC. So it's a competitive algorithm. Off-policy MDPO has a better sample efficiency than on-policy MDPO. This is not surprising. It's consistent with the common belief. Off-policy MDPO has a much higher wall clock time than on-policy MDPO. Again, this is consistent because you're updating more often than what you are updating in on-policy case. And then we did this study of regularized MDPO and adding the Sallis entropy, and whether this helps or not. The experiments show some effect, but this is far from being done. We need to understand this better. This actually is a nice summary in terms of comparison of MDPO with TRPO and PPO in terms of wall clock time, performance, and number of hyperparameters. As you can see, MDPO has less hyperparameter than PPO and TRPO. Its performance is similar to TRPO, but it's much better than PPO. If you add the code level optimization and stop at the appropriate time, then PPO becomes much more competitive in terms of performance. In terms of wall clock time, we are very similar to PPO, but much better than TRPO. And this is not again surprising because TRPO has that kind of enforcing the constraint that it's doing. But this is a nice, very overall comparison between this. So what is basically in this work is we basically learned two things from this work. One is there is a way that we can simply apply mirror descent and find a scalable RL algorithm. As you can see, our algorithm is very simple. You're just doing mirror descent, but instead of solving the optimization problem with iteration, you're just solving it approximately by taking multiple gradient step towards the optimal point. So an algorithm coming from simply from an optimization phenomena performs as well as many of the well-known algorithms in the literature. And also all these studies, both experimental and looking at these equations, shed some light on why these TRPO, PPO, and soft actor critic algorithms are working well, and how we can explain them from, again, lens of optimization. So to me, was interesting, for example, when we could find an explanation for SAC from the trust region point of view, which you're enforcing instead of some proximity enforcement, you are enforcing explorativeness. Then you say, okay, to remain explorative, don't move away too much from uniform policy. And that was basically the whole point. As I said, the paper has been accepted this year at ICLR. The version of the paper is on arXiv. We have a project webpage for this. We have a blog post. These days, apparently blog posts are important. And then we have also the code and everything on GitHub in order to run and see how things work. Thank you very much. And I don't know if we have time. I'm sorry that I went a little bit over time, but would be happy to answer more questions.
Well, thank you, Mohammad, for the great talk. No, I think we are right on time, and we have a few minutes for a few questions from the audience. So please feel free to write in chat or unmute yourself and ask the question directly from Mohammad.
I'm trying to look at the chat and see whether.
Yeah. So I think that there's a question about the relation between entropy and relaxation to trust region methods.
I don't think entropy has much to. So if you're saying entropy, meaning you're talking about because we use entropy in two different places. One, we use entropy to define the Bergman divergence and to define the form of the trust region. The other use of entropy was between hard and soft MDPs. So I'm not sure which use of entropy you're referring to here, because entropy was used in two different places. I don't know who asked the question,
yeah.
but
I think,
that's important to discriminate.
Yes.
The first one, in the first one, basically, it's not relaxing trust region. Entropy defines the trust region or basically that kernel of the Bergman defines the trust region. If you choose it as Euclidean, then your trust region is Euclidean distance. If you choose it as entropy, then it becomes the trust region defined form KL. And we also use this Salis business, which is another form of defining this trust region. So can you tell me about MPO and VMPO? What is happening in those algorithms? I'm sure they are related, because this is, if I'm not mistaken, these are mirror descent policy optimization algorithms. Probably they are related. I don't know the details of these algorithms, but I'm not surprised that there are some similarities. But I think probably answering this question requires sitting down and looking at the equations of both algorithms. But I wouldn't be surprised if there are similarities. As I told you, even when we read the paper, the PPO paper, which, as you know, PPO has never been published paper, the first part of the PPO, there is an algorithm that they propose and they throw it away. And basically they propose bash and throw away, which has some similarities with this algorithm. So as you see, the concept is very simple. I'm not surprised if people have thought about it and developed it. So
yeah. So perhaps I can also ask a question. So you used SGD updates to approximate the inner optimization of the mirror descent update. So I was wondering if you tried more accelerated algorithms, I don't know, for instance, SGD with momentum or SVRG type algorithms that incorporate variance reduction techniques to accelerate convergence.
No, we haven't done anything fancy there. Basically, we did the same thing for update. We did the same thing that TRPO and PPO are. Update means in terms of choice of. I shouldn't say that, because TRPO has a different way of selecting the step size. But in terms of using, variance reduction techniques and stuff, no.
Thank you.
Any other question? So yeah, the one thing is that we are currently looking at is better understanding of this notion of the choice of entropy and what is the role of the Salis entropy methods. Because one thing that I see, probably what I say is not going to be helpful for most of you. If you're doing things in online learning, maybe you have some better understanding what I'm saying, but the value of this Q and the way that it works better in RL is not consistent with the value of Q for the Sallis entropy that works well in the online learning literature. And this is a little bit puzzling to me, but I don't have any good answer for it. So that's also, for example, to be very simple, the Q value that works well in RL, at least in our experiments, was between 1 and 2. But in the theory of online learning algorithm, Q equal to half is the optimal value that is used. And I don't know how to answer that question, what's going on. Something is changing in these two formulations. And so that's one of the also question that I would like to have a better understanding, which is related to the choice of the entropies.
Yeah, so it seems there is another question.
Can you hear me? Is it?
Yes.
Yeah, I have a question. You have a penalty term of KL divergence in your update, and I was just wondering, like, do you approximate it to certain order, or do you take exact KL divergence? So how do you evaluate it in your experiments?
So in the deep reinforcement learning literature these days, the policy class is usually a Gaussian policy class represented by neural network. For them, there is a closed form solution for this KL. You're absolutely right. If we go fancier and go to more general classes of policies, that could be an issue. But that can be done easily when you restrict yourself to policy classes, Gaussian policy classes.
Okay. And maybe I missed in the starting, what was the motivation to go for reverse KL divergence instead of forward one? Or like,
so reverse, actually, the motivation was because this is what is happening in the mirror descent. Actually, we just followed what is happening in mirror descent. But there are some algorithms out there in RL that they are using the forward direction. And there are some justifications for both sides. And that's also another good question, that which direction is going to work better in practice, or can be, I shouldn't say which one works better in practice, because depending on application, the answer may go either way, but can we say something a little bit more fundamental and theoretically motivated about the choice of the direction of KL? But the choice that we have in our algorithm is what's happening in standard mirror descent, which is the reverse order.
Okay. Okay.
But this is also one of the good questions. If you are interested in this area, Nicolas Laroux has a couple of papers in this general area. He talks about the choice of the direction of the KL, which might be useful.
Okay. Yeah, thanks.
There is also a paper by Dale Shorman's group about this that we compared. We talked about it in our paper. Actually, I had it on my slides. I removed it because of time. But still, the answer is not very clear.
Okay, I see. Okay, thank you very much.
Yeah. Thank you. So it seems we are out of time. So I would like to thank Mohammad again for the great talk, and also everyone for attending ICON seminar today. And yeah, I hope you have a good rest of the day.
And thank you very much for inviting me and listening to the talk. If you have any question that I couldn't answer, you have my email address. Send me an email. We'll be happy to talk more. Thank you.
Yeah. Thank you. Thank you, everyone.